I'm here this afternoon to present a topic seminar to you. The effect of stereochemistry on biological activities with example. Introduction. Stereochemistry is a branch of chemistry that studies the spatial arrangement of atoms within molecule and how these arrangements affect the chemical and the physical property of compound. It focuses on the stereoisomer, which are molecule with the same molecular formula and the connectively built but different three-dimensional orientation, such as enantiomer and the stereomer. Importance of stereochemistry in biological activities. Number one, we have pharmacology activities, we have toxicity and the side effects. Number two, we have metabolism and pharmacokinetics. Number four, we have drug development and regulation. And on number five, we have natural products and the biological pathway. Back to number one, pharmacological activities. Stereoisomer, particularly enantiomer, mirror image. What is it we mean by the enantiomer? When a molecule has something like this, I have something like I have L enantiomer and what's it called D enantiomer. It's like mirror. For example, now if you have a compound like this, like let me use something like this. You have something like this. Maybe this one hydrogen. You have nitrogen here. Yeah. You have another compound. You can put something like this, and then it's in the mirror form. We now have another one here like this. We have now nitrogen. Yeah. We have the hydrogen. And this is what they call enantiomer. And that's a physical pharmacology activity stereoisomer. Particularly enantiomer mirror image stereoisomer can exhibit different affinity for biological target. For example, the S enantiomer of the anticoagulant drug warfarin is significantly more potent than the R enantiomer in the inhibiting vitamin K epoxide reductase, impacting its therapeutic efficacy. This stereospecific arise because receptor and enzyme have chiral active sites that particularly bind to enantiomer over other. What do you mean? What do they mean by chiral activities? This is the what's it called? Like this is the chiral compound now, and this is the chiral something like what is the chiral compound? The chiral compound is a compound that binds with what's it called? The different other group with a central carbon. It's called chiral compound. Also, number two, they have toxicity and side effect. Stereochemistry can influence the toxicity of compound. A notable example is a thalidomide, where the R enantiomer is a safe sedative, but the S enantiomer cause severe teratogenic effect. Overview of how stereochemistry influence drug activities. Stereochemistry, the study of three-dimensional arrangement of atoms in a molecule, play a critical role in determining the pharmacological activities, efficacy, and the safety of a drug. The spatial orientation of a molecule can significantly affect how it interacts with biological targets, such as enzyme, receptors, or ion channel. This overview explores the influence of stereochemistry of drug activity, focusing on chirality, as I said earlier, enantiomer, and their implication in pharmacokinetic and pharmacodynamic. Basic concept of stereochemistry relevant to biology. Number one, we have chirality, we have enantiomer and biological activity. Number two, we have optical activities, and number four, we have isomerism in molecular. Number one, chirality. Chirality refers to a molecule property of being non-superposable on its mirror image, often due to a carbon atom chiral center. This is chiral center. Bonded to four different groups. It's bonded with four different groups, as I said earlier. Chiral molecule such as amino acid and sugar exist as enantiomer mirror image with identical chemical composition but different spital arrangement. In biology, chirality is crucial because enzyme and receptor are stereospecific, typically interact with only one enantiomer. For example, L-amino acid are predominantly used in protein, while the amino acid are rare. Number two, enantiomer and biological activity. Enantiomer can have vastly different biological effects due to their stereochemical difference. For instance, the drug thalidomide has two enantiomer. Number one is therapeutic, while the other cause severe birth defects when administered as a racemic mixture. Number medicine in biomolecule. We have amino acid and carbohydrate, we have and protein under it. Amino acid. Most amino acid in the potent are L enantiomer. The chirality are the carbon determine the fit into enzyme active site, affecting structure and function. Carbohydrate. So as glucose D exists as blue as Z or L enantiomer, with D sugar dominating in biological system. The stereochemistry of glycoside bond also influence polysaccharide structure. Importance in biology. Stereochemistry govern molecular recognition, enzyme function, and drug efficacy. The homochirality of life is a fundamental mystery in the origin of life, suggesting stereochemical constraint sharp biochemical evolution, mechanism of stereochemical influence biological activity. The cell is a higher sensitivity to stereochemistry because receptors are composed of protein with a configuration. Enantiomer of a drug. Enantiomer of a drug may exhibit binding abilities due to their distinct spital arrangement, which affects how their activity. Enantiomer of a drug may bind effectively to a receptor, eliciting a therapeutic response, while the other may inactive or even antagonistic due to poor fit. Examples are highly specific recognition with the correct functional configuration. This is an active site is specific to substrate stereochemistry. For instance, amino acids are preferentially in one active process, while the amino acids are typically not recognized by most enzymes. Number three, the metabolic pathway of the drug is modified by stereochemistry as metabolism enzymes such as cytochrome are stereoactive. May be metabolized at different rates of or through the same pathway, leading to variation in the clearance, half-life, and potential toxicity. For instance, how enantiomer of warfarin is metabolized more rapidly by cytochrome P450 enzyme than the enantiomer resulting in different anticoagulant potency, factor that influencing stereochemical effects. Number one, we have a receptor stereospecific. We have enzyme substrate interaction. Number two, we have physiochemical properties. Receptor specific. Number one, receptors are often have rigid chiral binding sites that Vol1 seen a reaction of L-dopamine for essence of a substrate. It can catalyze reaction with an enantiomer due to stereochemic active site. Example of stereochemistry activity. One, we have thalidomide. Thalidomide is a glorious example of how stereochemistry could drive different pharmacology atoms as a representation of atom and S-thalidomide. Enantiomer is an effective and emetic partially treating more sickness. Enantiomer is a therapeutic for severe malformation when administered during pregnancy. In fact, the development disaster underscore the need for synthesis and testing, leading to stricter requirement for child drugs. Also, we have also we have a protopump introduced acid related is a routinely mixture of and S and that and the enantiomer yes mark as a is a more at treating adding pressure impacts greater action but also pharmacokinetic profile with two plants and higher availability than basic omeprazole. Thank you for studying nuclear and magnetic spectroscopy, see this compilation so computational methods such as density functional therapy and the molecular dynamics stimulate predict technical outcome of reaction and the molecular conformation. These tools complement experimental data by modeling energy difference between stereoisomer. Pharmaceutical industrial and chirality. The point of chirality in the development. Chiral drug constitutes a significant portion of the global market, with over 50% of market drug being chiral and exhibit different pharmacological effects. One enantiomer may be therapeutic active, while the other may be for example, when the enantiomer like that of levofloxacin and the levofloxacin. Levofloxacin is a D enantiomer, while levofloxacin is a what's it called L enantiomer. The L enantiomer is more effective than D enantiomer than D ofloxacin. Ofloxacin is more active than ofloxacin or enantiomer. Drug synthesis of the single enantiomer known as enantiopure drug has been a major focus of pharmaceutical research. Traditional methods often produce remedy mixtures requiring costly and inefficient separation techniques. Advances in catalyzed and biocatalysis have enabled the production of enantiopure compounds with high efficacy. Challenge and future perspective. Challenge and future perspective. Challenge in stereochemistry and biological activity. Number one, we have complexity of selective synthesis. One of the primary challenges is leveraging stereochemistry for biological application is the difficulty in synthesis stereospecific compound. The synthesis of a single enantiomer with high purity often require complex and costly process such as chiral catalysis or solution techniques. For instance, the production of enantiomer drug like thalidomide, while one enantiomer is therapeutic and the other is teratogenic. Highlighting the available of and cost-effective method remain a significant hurdle. Number two, we have understanding stereospecific interaction. We have regulatory and safety con. We have analytic limitation and we have analytic limitation. Future perspective. Advancement in compilation modeling. The development of advanced computation tools such as a molecular dynamic simulation and machine learning analog, offering promising avenue for predicting stereospecific interaction. These tools can model the binding of stereoisomer of biological targets. Also, we have innovation in chiral synthesis. We have personalized medicine and stereochemistry, improved analysis techniques. In my conclusion, stereochemistry, stereochemistry, the study of the three-dimensional arrangement of atom in a molecule, play a critical role in determining